解答题。然后它有分文理，大概就是我科。
Well, first of all, welcome back to today's class of MATH113, Section 7, Applications of Mathematics in Today's World. Today is day number 16 in week number 8. And so, let's have a review on what we are up to as of last week, or basically as of last class on Tuesday. Well, so far, if you look at what we have done so far, we have gone through 7 important lectures from the MIT courseware, which is presented by Professor David Jervisons, with the specific topics on derivatives, slopes, velocity, rate of change. And the second lecture, limits, continuity, and some trigonometric limits. And then when we come to lecture number 3, we deepen our understandings on the derivative, slope, velocity, and rate of change. And so in lecture number 4, we come to the 3 important rules in differentiations: the product rule, the quotient rule, the chain rule, and a little bit of the techniques of higher derivatives. And lecture number 5 deals with implicit differentiations and some inverse functions. And in our last week, last Friday, including the past on Tuesday, we explore the exponential functions together with the logarithmic functions. And so we know how to do logarithmic differentiations, but we did not talk about hyperbolic functions. Well, today, if you look at our calendar, okay, from the website, we should have finished the lessons on day number 15, which include linear approximations, which is the applications of derivative, examples of linear approximations, the quadratic approximations, and examples of quadratic approximations. And then we come to sketching graphs using polynomials and rational functions and some general strategies. Now, because of the shift in emphasis of our previous 2 classes, I've actually reordered these number of sections for next week. What we are going to do today is basically included in a review on what we have done on a derivative, but we come back to something that is very important, that is called the maximum and the minimum points. Okay, if we look at the specific review on Professor Gilbert Stroud's highlight of calculus, which is given almost in every week before the class activity, you know that so far we have gone through the first one, the big picture of calculus, the exponential functions, and also the big picture of a derivative, all right? But the maximum and minimum, as well as the second derivative, we have actually not touched them when we should have touched them based on the reference text. So today, we are going to stop day number 15's material and push it to next week. And we would like to come back to the applications of the derivative so that you will have a better understanding on sketching the curve. All right? So, the maximum and the minimum point in a particular curve. At the top and bottom of a curve, we call the max and the minimum. The slope is equal to 0. Okay? The slope is equal to 0. And when we come to the higher derivative, such as the second derivative, we have to show whether the curve will, in a sense of sketching it bending downward or bending upward, depending on the maximum point or the minimum point we are looking at. So today, we would like to revisit this part of the calculus lessons that we have not covered in the past couple of weeks by going through a review on this topic to be presented by Professor Gilbert Stroud. And after that, I will show you a slightly different approach using the very interesting video examples from the Khan's Academy to help us to understand the meanings of critical points. Okay? So we're going to have a very rich class today. But remember, we have spent time in the past lessons, as well as last Friday, on exploring the exponential functions and the logarithmic function. And so far, the very interesting thing on exponential series and geometric series, these should not be something new to you at this point. Okay, now let's get started with Professor Gillenstrand's max and minimum for the second derivative. Please take a look at the notes first. It's very important for us to know, to recognize the shape of the curve based on the discovery of the maximum.
Right. Well, hope you're ready for second derivatives. They come, we don't go higher than that in many problems, but the second derivative is an important, the derivative of the derivative is an important thing to know, especially in problems with maximum and minimum, which is the big application of derivatives. To locate a maximum or a minimum and to decide which one it is. And I can tell you right away, locating a maximum, minimum is the first derivative's job. The first derivative is 0. If I have a maximum or a minimum, and we'll have pictures. Somewhere in the middle of my function, I'll recognize by derivative equals 0, slope equals 0, that the function is leveling off, either bending down or bending up. Maximum or minimum. Okay, and it's the second derivative that tells me which it is. The second derivative tells me the bending of the graph. Okay, so we now will have 3 generations. The big picture of calculus started with 2 functions, the distance and the speed, and we discussed in detail the connection between them. How to recover the speed if we know the distance. Take the derivative. Now comes the derivative of the speed, which in that language, in the distance, speed, time language, the second derivative is the acceleration. The rate at which your speed is changing, the rate at which you're speeding up or slowing down. And this is the way I would write that. If the speed is the first derivative, df dt, this is the way you write the second derivative, and you say d second f dt squared. D second f dt squared. Okay, so that's the, you could say, the physics example. Distance, speed, acceleration. I say physics because, of course, acceleration is the A in Newton's law, F equal ma. For a graph, like these graphs here, I won't specially use those physics words, I'll use graph words. So I would say function 1 would be the height of the graph. And in this case, that height is y equal x squared. So it's a simple parabola. Here would be the slope. I would use the word slope for the second function. And the slope of y equal x squared, we know, is 2x. So we see the slope increasing. And you see on this picture, the slope is increasing. As I go, as x increases, I'm going up more steeply. Now, it's the second derivative. And what shall I call that? Bending. Bending is the natural word for the second derivative on a graph. And what do the derivative of 2x is 2, a constant, a positive constant, and that positive constant tells me that the slope is going upwards and that the curve is bending upwards. So in this simple case, we connect these three descriptions of our function. It's positive, its slope is positive, and its second derivative, bending, is positive. And that gives us a function that goes like that. Now, let me go to a different function. Let me take a second example now. An example where not everything is positive. So I'll take, let's make it familiar. Take sine x. So sine x starts out like that. So this is a graph of sine x up to 90 degrees, pi over 2. So that's y equals sine x. Okay, what do you think about its slope? We know the derivative of sine x, but before we write it down, look at the graph. The slope is positive, right? But the slope starts out at 1. Better make it look a little more realistic. That's a slope of 1 there. The slope starts at 1, and the slope drops to a slope of 0 up there. So a slope of 1, I see here as a 1. Here I'm graphing y prime. The y dx I sometimes write as y prime, just because it's shorter, and particularly it'll be shorter for a second derivative. So y prime, we know the derivative of sine x is cos x, which is pretty neat, actually. That we start with a familiar function and then we get its twin, its other half. And the cosine is the slope of the sine curve, and it starts at 1, the slope of 1, and it comes down to 0, as we know the cosine does. So that's a graph of the cosine. And now, of course, we have 3 generations. I'm going to graph y double prime. Let me put it up here. Y double prime, the second derivative. The derivative of the cosine of x is minus sine x. Okay, let's just, from the picture, what am I seeing here? I'm seeing a slope of 0. I'm taking now the slope of the slope. So here it starts at 0. The slope is downwards. So the second derivative is going to be negative. Oh, and it is negative. Minus sine x. So the slope starts at 0 and ends at minus 1. So, because that now comes down at a slope of a negative slope. The slope is negative, I'm going downhill, and that's a graph of the second derivative. And which way is our function bending? It's bending down. As I go along, the slope is dropping. And I see that in the slope curve, it's falling. And I see it in the bending curve because I'm below 0 here. This is bending down. Where that one was bending up. I could introduce the word convex for something that bends upwards, and bending down I could introduce the word concave. But those are just words. The graphs are telling us much more than the words do. Okay, so do you see that picture, bending down but going up? So the slope is positive here, but the second derivative, the slope is dropping. So the second derivative, and you have to pay attention to keep them straight. The the second derivative is telling us that the original one is bending down. Okay. Let me continue these graphs just a little beyond 90 degrees, pi over 2, because you'll see something interesting. So what happens in the next part of the graph? So this is going, the sine curve, of course, continues on its way downwards. So the slope is going negative, as I know the cosine curve will do. The cosine curve will come like that. The slope down to -1. The slope, you see here, the slope is negative. So on this slope graph, I'm below 0. And the slope is 0. Let me put a little mark at these points here. Yeah, at these 3 points. So that was important. Those are important points. In fact, that is a maximum, of course. The sine curve hits its maximum at 1. At that point, when it hits its maximum, what's its slope? When you hit a maximum, you're not going up anymore. You haven't started down. The slope is 0, right there. What's the second derivative? What's the bending at a maximum? The bending tells you that the slope is going down, so the bending is negative. The bending is negative at a maximum. Good. Okay. Now I'm going to continuing this sine curve for another 90 degrees, the cosine curve, and I'll continue the bending curve. So that I have minus sine x, which will go back up. Okay. Now what? Now what? And then, of course, it would continue along. Okay, there's something interesting happening at 180 degrees, at pi. Can I identify that point? So there's 180 degrees. Something's happening there. I don't quite know how to say what yet, but something's happening there. It's got to show up here, and it has to show up here. So whatever is happening is showing up by a point where y double prime, the second derivative, is 0. Why, what? That's my new little observation. Not as big a deal as maximum or minimum. This was a max here. And we identified it as a max because the second derivative was negative. Now I'm interested in this point. Can you see what's happening at this point as far as bending goes? This curve is bending down. But when I continue, the bending changes to up. This is a point where the bending changes. The second derivative changes sign, and we see it here. Up to this square point, the bending is below 0. The bending is downwards as I come to here. But then there's something rather special. That you see, can I try to blow that point up? Here the bending is down, and there it turns to up, and right in there with the this is called, so this is my final word to introduce, inflection point. Don't ask me why. An inflection point is a point where the second derivative is 0. And what does that mean? That means it's at that moment, it stopped bending down and it's going to start bending up. The second derivative is passing through 0. The sign of bending is changing. It's changing from concave here to convex there. That's a significant point on the graph. Not as big a thing as the max or the min that we we had over there. So let me draw one more example and identify all these different points. Okay, so here we go. I drew it ahead of time because it's got a few loops and I wanted to get it in good form. Okay, here it is. This is my function, x cubed minus x squared. Well, before I look at the picture, what's the first calculus thing I do? I take the derivative. Y prime is the derivative of x cubed is 3x squared minus the derivative of x squared, which is 2x. And now, today, I take the derivative of that. I take the second derivative, y double prime. So the second derivative is the derivative of this. X squared is going to give me 2x, and I have a 3, so it's altogether 6x. And minus 2x, the slope of that is minus 2. Right? Cubic, quadratic, linear, and if I cared about y triple prime, which I don't, constant. And then the fourth derivatives and all the rest would be 0 for this case. Okay, now somehow those derivatives, those formulas for y, y prime, y double prime should tell me details about this graph. And the first thing I'm interested in, and the most important thing, is max and min. So let me set y prime to be, which is 3x squared. I'll set the minus 2x. I'll set it to be 0 because I want to look for max or min. And I look for both at the same time by setting y prime equals 0. And then I find out which I've got by looking at y double prime. So let me set y prime to be 0. What are the solutions? Where are the points on the curve where it's stationary? It's not climbing and it's not dropping. Well, I can see them on the curve here. That is a point where the slope is 0, and I see one down here. There is a point where the slope is 0, but I can find them with algebra. I solve 3x squared equal to 2x, and I see it's a quadratic equation. I expect to find two roots. One of them is x equals 0, and the other one is what? If I cancel those x's to find a non-zero, canceling those x's leaves me with 3x equal 2 or x equal 2/3. Yeah, and that's what our graph shows. Okay. Now we can see on the graph which is a max and which is a min. And by the way, let me notice, of course, this is the max. But let me just notice that it's what I would call a local maximum. It's not the absolute top of the function, because the function later on is climbing off to infinity. This would be a maximum in its neighborhood. So a maximum, and it's only a local max. And what do I expect to see at a maximum? At x equals 0. I expect to see the slope 0 at x equals 0, which it is. Check. And at a maximum, I need to know the second derivative. Okay, here's my formula. At x equals 0, I see y double prime, if x is 0, is minus 2. Good. Negative second derivative tells me I'm bending down, as the graph confirms, and the place where the slope is 0 is a maximum and not a minimum. What about the other one? What about at x equal 2/3? At that point, y double prime, looking at my formula here for y double prime, is what? 6 times 2/3 is 4, minus 2 is plus 2. 4 minus 2 is 2. So this will be, this is positive, so I'm expecting a min. At x equal 2/3, I'm expecting a min. And of course, it is. And again, it's only a local minimum. The derivative can only tell you what's happening very, very close to that point. The derivative doesn't know that over here, the function is going further down. So this is a min, and again, a local min. Okay. Those are maximum and minimum when we know the function. Oh yeah, I better do the inflection point. You remember what the inflection point is? The inflection point is when the bending changes from up to here, I see that bending down. From here, I see it bending up. So I will not be surprised if that's the point where the bending is changing and 1/3 is the inflection point. And now how do we find an inflection point? How do we identify this point? Well, y double prime was negative, y double prime was positive. At that point, y double prime is 0. This is an inflection point, and it is. At x equal to 1/3, at x equal 1/3, I do have 6 times 1/3. 2, subtract 2, I have 0. So that is truly an inflection point. And now I know all the essential points about the curve. And this is the kind of quantity, these are the quantities of, oh, say you're an economist, you're looking now at the statistics for the US economy or the world economy. Okay, I suppose we had a local maximum there, happy time, a little while ago. But it went downhill, right? If y is, say, the gross product for the world, or gross national product, it started down. The slope of that curve was negative. The bending was even negative. It was going down faster all the time. Now, at a certain moment, the economy kept going down, but you could see some sign of hope. And what was the sign of hope? It was the fact that it started bending up. And probably that's where we are as I'm making this video. I suspect we're still going down, but we're bending up, and at some point, hopefully tomorrow, we'll hit minimum and start really up. So I don't know, I would guess we're somewhere in there, and I don't know where. If I knew where, mathematics would be even more useful than it is, which would be hard to do. Okay, so that's an example of how the second derivative comes in. Now, I started by giving this lecture the title Max and Min. And saying those are the biggest applications of the derivative. Set the derivative to 0 and solve. Locate maximum points, minimum points. That's what calculus is. Many of the word problems, most of the ones I see in use, involve derivative equals 0. Okay, so let me take a particular example. So these were graph simple functions, which I chose. Sine x, x squared, x cubed minus x squared. Now let me tell you the problem, because this is how math really comes. Let me tell you the problem, and let's create the function. Okay, so it's the problem I faced this morning and every morning. I live here, so here's home. And there is the Mass Pike is the fast road to MIT. So let me put in the mass pipe here. And let's say that's MIT. And I'm trying to get there as fast as possible. Okay. So, for part of the time, I'm going to have to drive on city streets. I do have to drive on city streets. And then I get to go on the mass pike, which is, let's say, twice as fast. The question is, where should I go directly over to the fast road and then take off? Let's take off on a good morning. The mass pike could be twice as slow, but let's assume twice as fast. Should I go straight over? Probably not. That's not the best way. I should probably pick up the mass pike on some road. I could go directly to MIT on the city streets at the slow rate. Say 30 miles an hour or 30 kilometers an hour and 60. So speeds 30 and 60 as my speeds. Okay. So, and now I should have put in some measure. Let's call that distance A, whatever it is. Maybe it's about 3 miles. And let me call this, so that's the direct distance. If I just went direct to the turnpike, I would go a distance A at 30 miles an hour, and then I would go a distance, so I call that B, at 60. So that's one possibility. But I think it's not the best. I think better to, and you know better than me, I think I should probably angle over here and pick up this. My question is, where should I join the mass pike? And let's, so we get a calculus problem, let's model it. Suppose that I can join it anywhere I like, not just at a couple of entrances. Anywhere. And the question is, where? So calculus deals with the continuous choice of x. So that is the unknown. I could take that as the unknown x. That was a key step, of course, deciding what should be the unknown. I could also have taken this angle as an unknown, and that would be quite neat too. But let me take that x. So this distance is then b minus x. So that's what I travel on the mass pike. So my time to minimize. I'm trying to minimize my time. Okay. So on this mass pike, when I travel at 60, I have distance divided by 60 is the time, right? Am I remembering correctly? Let's just remember. Distance is speed times time. That's the one we know. And then if I divide by the speed, the time is the distance divided by the speed. The distance divided by the speed on the pike. And now I have the distance on the city streets. Okay, so that speed is going to be 30. So the time is going to be a bit longer for the distance. And what is that distance? Okay, that was A, this was X. Pythagoras is the great leveler of mathematics. That's the distance on the city streets. And now, what do? I've got an expression for the time. This is the quantity I'm trying to minimize. I minimize it by taking its derivative and set the derivative to 0. Take the derivative and set the derivative to 0. So now this is where I use the formulas of calculus. So the derivative. Now I'm ready to write the derivative. And I'll set it to 0. So the derivative of that, b is a constant, so I have minus 1/60th. Is that okay? Plus whatever the derivative of this is. Well, I have a 30th. I take the constant first. Now I have to deal with that expression. That is some quantity square root. The square root is the 1/2 power. So I have 1/2 times this quantity to one lower power. That's the minus 1/2 power. That means that I still have a square root, but now it's a minus 1/2 power. It's down here. And then the chain rule says, don't forget the derivative of what's inside, which is 2x. Okay, depending what order you've seen these videos and read text, you know the chain rule or you see it now. It's a very, very valuable rule to find derivatives as the function gets complicated. And the thing to remember, there will be a proper discussion of the chain rule. It's so important. But you're seeing it here, that the thing to remember is take also the derivative of what's inside, the a squared plus x squared, and the derivative of the x squared is the 2x. Okay, and then I have to set to 0. And of course I'm going to cancel the 2's. And I'll set it to 0. What does that mean, set to 0? Here's something minus, here's something plus. I guess what I really want is to make them equal. When the 1/60th equals this messier expression, at that point, the minus term cancels the plus term. I get 0 for the derivative. So I'm looking for derivative equals 0. That's my equation now. Okay, now I just have to solve it. All right. Let's see. If I wanted to solve that, I would probably multiply through by 60. Can I do this? I'll multiply both sides by 60. That will cancel the 30 and leave an extra 2, so I'll have a 2x here. And let me multiply also by this miserable square root that's in the denominator to get it up there. I think that's what I've got. That's the same equation as this one, just simplified. Multiply through by 60, multiply through by square root of a squared plus x squared, and it's looking good. All right, how am I going to solve that? Well, the only mess up is the square root. Get rid of that by squaring both sides. So now I square both sides and I get a squared plus x squared, and the square of 2x is 4x squared. All right, now I have an equation that's way better. In fact, even better if I subtract x squared from both sides. My equation is telling me that a squared should be 3x squared. In other words, this good x is, now I'm ready to take the square root and find x itself. So put the 3 here, take the square root. I'm getting a over the square root of 3. So there is a word problem, a minimum problem, where we had to create the function to minimize, which was the time, trying to get to work as quickly as possible. After naming the key quantity x, then taking the derivative, then simplifying, and it took a little, that's where the little work of calculus comes in. In the end, getting something nice, solving it, and getting the answer a over square root of 3. So we now know what to do driving in, if there's an entrance where we want to get it. And actually, it is a beautiful answer. If this is a over the square root of 3, this will turn out to be 30 degrees, pi over 6. I think. Yeah, I think that's right. So that's the conclusion from calculus. Drive at a 30-degree angle, hope that there's a road going that way. Sorry about that point. And join the turnpike, and probably the reason for that nice answer, 30 degrees, came, I can't help but imagine that because I chose 30 and 60 here, a ratio of 1 to 2, and then somehow the fact that the sine of 30 degrees is 1/2, those two facts have got to be connected. So I could, if I change these 30 and 60 numbers, I'll change my answer, but basically the picture won't change much. And there's another little point to make to really complete this problem. It could have happened that the distance on the turnpike was very small, and that this was a dumb move. That 30-degree angle could be overshooting MIT, if MIT was like there. So that's a case in which the minimum time didn't happen where the derivative bottomed out. If MIT was here, the good idea would be go straight for it. Just the extra part on the turn, you wouldn't drive on the turnpike at all. And that's a signal that somehow in the graph, which I didn't graph this function, but if I did, then this stuff would be locating the minimum of the graph. But this extra example where you go straight for MIT would be a case in which the minimum is at the end. And of course that could happen. You could have a graph that just goes down and then it ends. So the minimum is there, even though the graph looks like it's still going down, the graph ended. What can you do? That's the best point there is. Okay, so that is can I recap this lecture? Coming first over here. So the lecture is about maximum and minimum, and we learned which it is by the second derivative. So then we had examples. There was an example of a minimum when the second derivative was positive. Here was an example of a local maximum when the second derivative was negative. Here, with the sine and cosine, those are nice examples. And it takes some patience to go through them. I suggest you take another simple function, like start with cosine its. Find its maximum, find its minimum, find its inflection points. So the inflection points are where the bending is 0, because it's changing from bending one way to bending the other way. We didn't need an inflection to test, so actually I didn't complete the lecture, because I didn't compute the second derivative and show that this was truly a minimum. I could have done that. I would have had to take the derivative of this, which would be one level messy, and look at its sine. I wouldn't have to set it to 0. I would be looking at the sine of the second derivative. And in this problem, it would safely come out positive sine, meaning bending upwards, meaning that this point I've identified by all these steps was truly the minimum time, not a maximum. Okay, that's a big part of important calculus applications.
What I would like you to do is to complete the steps here, because as Professor Gilbert Strand said, he did not calculate the second derivative to test it. I would like you to do these verifications. Now take this particular chunks of equations, all right, and calculate the second derivative and check the sign of the second derivative and to see if this is the maximum or the minimum. Okay? Can you just try, do you see the formulations here? This is the time is equal to b minus x divided by 60 plus square root of a squared plus x squared divided by 30. And that is the expressions of the time. So expression of time means what? Well, that's the first derivative, right? So calculate the second derivative and see if you can verify the sign. Now, from the lessons we know that based on the sign of the second derivative, If the sign of the second derivative is positive, it means it's a minimum point, it's bending upwards. If the sign of the second derivative is negative, it means it's a maximum point because it's bending downward. Now, can you try to see if you can verify this? And of course, you can start on your own one more time. This is a very typical application of derivative. It's that this is the main road, right? This is the mass transit road, and your car is somewhere here. You want to jump this mass transit road in such a way that you're going to travel the minimum distance, with the minimum time, better say, with the travel the distance with the minimum time. So this time, minimum means set the first derivative to 0, right? So see if you could verify this a little bit, and based on your knowledge of the derivative so far. Then try 5 minutes time to see if you could basically go back and backtrack on this particular problem. And of course, we will search for not exactly the answers, but things like this is very important for you to carry forward in your midterm also in the next months of work, which is your project, all right? Oh, yes. Please make sure you let me know your team compositions. Many of you did not set your team compositions yet, but I will come back to this. Because starting next month, we will step into the last set of homework, the learning contract number 3, and then you have to do definitely teamwork, proposing questions, which is the applications of the mathematics you learn in a specific problem, all right? So you need to do it in team, just like in the second collections. Now the homework you do it in team. I know you know who are your member. Unfortunately, I do not know yet. I know you sit together. I know you're working homeworks together, but you need to let me know, all right? So do you understand this, all right? Think a little bit further, and so the reasons why I stopped the way of the lectures and push it back to next week is because I want you to see the basic applications of this derivative in calculus to solve some problems. All right? So of course, and I can backtrack a little bit. You want to see the specifics. Yes.
So let me take a particular example. So these were graphed simple functions, which I chose. Sine x, x squared, x cubed minus x squared. Now let me tell you the problem, because this is how math really comes. Let me tell you the problem and let's create the function. Okay, so it's the problem I faced this morning and every morning. I live here, so here's home. And there is the Mass Pike is the fast road to MIT. So let me put in the Mass Pike here. And let's say that's MIT. And I'm trying to get there as fast as possible. Okay. So, for part of the time, I'm going to have to drive on city streets. I do have to drive on city streets. And then I get to go on the Mass Pike, which is, let's say, twice as fast. The question is, where should I go directly over to the fast road and then take off? Let's take off on a good morning. The Mass Pike could be twice as slow, but let's assume twice as fast. Should I go straight over? Probably not. That's not the best way. I should probably pick up the Mass Pike on some road. I could go directly to MIT on the city streets at the slow rate. Say 30 miles an hour or 30 kilometers an hour and 60. So speeds 30 and and 60 as my speeds. Okay. So, and now I should have put in some measure. Let's call that distance A, whatever it is. Maybe it's about 3 miles. And let me call, so that's the direct distance. If I just went direct to the turnpike, I would go a distance A at 30 miles an hour, and then I would go a distance, so I call that B, at 60. So that's one possibility. But I think it's not the best. I think better to, and you know better than me, I think I should probably angle over here and pick up this. My question is, where should I join the mass pipe? And let's, so we get a calculus problem, let's model it. Suppose that I can join it anywhere I like, not just at a couple of entrances, anywhere. And the question is, where? So calculus deals with the continuous choice of x. So that is the unknown. I could take that as the unknown x. That was a key step, of course, deciding what should be the unknown. I could also have taken this angle as an unknown, and that would be quite neat too. But let me take that x. So this distance is then b minus x. So that's what I travel on the mass pipe. So my time to minimize. I'm trying to minimize my time. Okay. So on this mass pipe, when I travel at 60, I have distance divided by 60 is the time, right? Am I remembering correctly? Let's just remember. Distance is speed times time. That's the one we know. And then if I divide by the speed, the time is the distance divided by the speed. The distance divided by the speed on the pipe. And now I have the distance on the city streets. Okay, so that speed is going to be 30. So the time is going to be a bit longer for the distance. And what is that distance? Okay, that was A, this was X. Pythagoras is the great leveler of mathematics. That's the distance on the city streets. And now, what do? I've got an expression for the time. This is the quantity I'm trying to minimize. I minimize it by taking its derivative and set the derivative to 0. Take the derivative and set the derivative to 0. So now this is where I use the formulas of calculus. So the derivative. Now I'm ready to write the derivative. And I'll set it to 0. So the derivative of that, b is a constant, so I have minus 1/60th. Is that okay? Plus whatever the derivative of this is. Well, I have a 30th. I will take the constant first. Now I have to deal with that expression. That is some quantity square root. Square root is the 1/2 power. So I have 1/2 times this quantity to one lower power. That's the minus 1/2 power. That means that I still have a square root, but now it's a minus 1/2 power. It's down here. And then the chain rule says, don't forget the derivative of what's inside, which is 2x. Okay, depending what order you've seen these videos and read text, you know the chain rule, or you see it now. It's a very, very valuable rule to find derivatives as the function gets complicated. And the thing to remember, there will be a proper discussion of the chain rule. It's so important. But you're seeing it here, that the thing to remember is take also the derivative of what's inside, the the a squared plus x squared, and the derivative of the x squared is the 2x. Okay, and then I have to set to 0. And of course I'm going to cancel the 2's. And I'll set it to 0. What does that mean, set to 0? Here's something minus, here's something plus. I guess what I really want is to make them equal. When the 1/60th equals this messier expression, at that point, the minus term cancels the plus term. I get 0 for the derivative. So I'm looking for derivative equals 0. That's my equation now. Okay, now I just have to solve it. And of course I'm going to cancel the 2's.
What I would like you to know is, he has not done the second derivative. And if he has done the second derivative, he needs to make use of the first derivative and do the second derivative, right? And because he erased the first derivative, towards the end he just said, I haven't done it. So, my suggestion to you minutes ago is to check if this is right, because if you got the second derivative, you can apply your understanding to see if the second derivative is positive or negative in a specific form. Well, anyway, I think with this repeat of the video, you could understand the formulations of the problem and the way that the problem has been manipulated to obtain solutions. And then you got the band down and the band up. Once again, if the second derivative is positive, it means it's a minimum form. If the second derivative is negative, it means the maximum form. So there is a rule such as that second derivative positive, minimum form, bending up. Second derivative negative, maximum form is bending down. So kindly remember that. And of course, you can repeat the video several times, particularly on those areas which does not seem to be very clear to you. Now, allow me to show you the very important points here today. That is, we need to go back to date number 11. Last time I said we will come back to this after you've learned exponential functions. Now these set of very important but easy to understand video help you to recapture the idea of the minimum, the idea of the maximum, and also the idea of the critical form. Actually, in Professor Gilbert Stratton's introductions minutes ago, when you see the video, he introduced you the idea of the local minimum and the local maximum. All right? So we're going to serve you a little bit of this by coming to this Khan's Academies video, and I hope you understand that. It takes you just minutes to go through the lessons. We're going to learn the ideas of the minimum and the maximum and critical point one more time with this video.
I've drawn a crazy looking function here in yellow. And what I want to think about is when this function takes on maximum values and minimum values. And for the sake of this video, we can assume that the graph of this function just keeps getting lower and lower and lower as x becomes more and more negative, and lower and lower and lower as x goes beyond the interval that I have depicted right over here. So what is the maximum value that this function takes on? Well, we can eyeball that. It looks like it's at this point. Looks like it's at that point right over there. So we would call this a global maximum. A global maximum. The function never takes on a value larger than this. So we could say that we have a global maximum at the point x naught. Because f of x naught is greater than or equal to f of x for any other x in the domain. And that's pretty obvious when you look at it like this. Now, do we have a global minimum point the way that I've drawn it? Well, no. This function can take on arbitrarily negative values. It approaches negative infinity as x approaches negative infinity. It approaches negative infinity as x approaches positive infinity. So we have, let me write this down, we have no global minimum. Now let me ask you a question. Do we have local minima or local maxima? When I say minima, it's just the plural of minimum, and maxima is just the plural of maximum. So do we have a local minima here, or local minimum here? Well, a local minimum, you can imagine, means that that value of the function at that point is lower than the points around it. So right over here, it looks like we have a local minimum. We have a local minimum. And I'm not giving you a very rigorous definition here, but one way to think about it is, we can say that we have a local minimum point at x1 is if we have a region around x1 where f of x1 is less than an f of x for any x in this region right over here. And it's pretty easy to eyeball too. This is a low point for any of the values of f around it right over there. Now, do we have any other local minima? Well, it doesn't look like we do. Now, what about local maxima? Well, this one right over here, let me do it in purple. I don't want to get people confused, actually. Let me do it in this color. This point right over here looks like a local maximum. Local, not locks, that would have to deal with salmon. Local maximum right over there. Local maximum. So we could say at the point x1, at the point x2, we have a local maximum point at x2 because f of x2 is larger than f of x for any x around a neighborhood around x2. I'm not being very rigorous, but you can see it just by looking at it. So that's fair enough. We've identified all of the maxima and minima, often called the extrema, for this function. Now, how can we identify those if we knew something about the derivative of the function? Well, let's look at the derivative at each of these points. So at this first point right over here, if I were to try to visualize the tangent line, we do that in a better color than brown. If I were to try to visualize the tangent line, it would look something like that. So the slope here is 0. So we would say that f prime of x naught is equal to 0. The slope of the tangent line at this point is 0. What about over here? Well, once again, the tangent line would look something like that. So once again, we would say f prime at x1 is equal to 0. What about over here? Well, here, the tangent line is actually not well defined. We have a positive slope going into it, and then immediately jumps to being a negative slope. So over here, f prime of x2 is not defined. Let me just write undefined. Undefined. So we have an interesting, and once again, I'm not rigorously proving it to you, I just want you to get the intuition here. We see that if we have some type of an extrema, and we're not talking about when x is at an endpoint of an interval, just to be clear what I'm talking about when I'm talking about x as an endpoint of an interval, we're saying, let's say that the function is, let's say we have an interval from there, so let's say a function starts right over there and then keeps going. This would be a maximum point, but it would be an endpoint. We're not talking about endpoints right now. We're talking about when we have points in between, or when our interval is infinite. So we're not talking about points like that or points like this. We're talking about the points in between. The points in between. So if you have a point inside of an interval, it's going to be a minimum or maximum, and we see the intuition here. If you have, so non-endpoint, min or max at, let's say, x is equal to a. So if you know that you have a minimum or maximum point, at some point x is equal to a, and x isn't the endpoint, x isn't the endpoint of some interval, this tells you something interesting, or at least we have the intuition. We see that the derivative at x is equal to a is going to be equal to 0, or the derivative at x is equal to a is going to be undefined. And we see that in each of these cases. Derivative is 0, derivative is 0, derivative is undefined. And we have a word for these points where the derivative is either 0 or the derivative is undefined. We call them critical points. We call them critical points. So for the sake of this function, the critical points the critical points are, if we can include x sub 0, we can include x sub 1. At x sub 0 and x sub 1, the derivative is 0, and x sub 2, where the function is undefined. Now, so if we have a non-endpoint minimum or maximum point, then it's going to be a critical point. But can we say it the other way around? If we find a critical point where the derivative is 0 or the derivative is undefined, is that going to be a maximum or minimum point? And to think about that, let's imagine this point right over here. So let's call this x sub 3. If we look at the tangent line right over here, if we look at the slope right over here, it looks like f prime of x sub 3 is equal to 0. So based on our definition of critical point, x sub 3 would also be a critical point, but it does not appear to be a minimum or a maximum point. So minimum or maximum point, that's not an endpoint, it's definitely going to be a critical point, but being a critical point by itself does not mean you're at a minimum or maximum point. So just to be clear, at all of these points, we're at a minimum or maximum point. We're at a critical point. All of these are critical points, but this is not a minimum or maximum point. In the next video, we'll start to think about how you can differentiate, or how you can tell whether you have a minimum or maximum at a critical point.
Do you got the idea? I just got 850 energy points after watching this video. With this video in place, you understand how to distinguish a maximum to be global or local, how to distinguish a minimum to be global. And you can also understand the meaning of critical points, which include those points where the derivative of a particular function is equal to 0, and also include where the derivative, the first derivative of functions, is to be undefined. Now, the next question is, how can you go from the critical point to tell if that point represents a maximum point or a minimum point? So,
let's say that f of x is equal to x times e to the negative 2x squared. And we want to find any critical numbers for f. So I encourage you to pause this video and think about, can you find any critical numbers of f? So assuming you give it a go at it, so let's just remind ourselves what a critical number is. So we would say c is a critical number of f, if and only if with two f's, short for if and only if f prime of c is equal to 0, or f prime of c is undefined. So if we look for the critical numbers for f, we want to figure out all the places where the derivative of this with respect to x is either equal to 0 or it is undefined. So let's think about how we can find the derivative of this. So let's see, f prime of x is going to be, well, let's see, we're going to have to apply some combination of the product rule and the chain rule. So it's going to be the derivative with respect to x of x, so it's going to be that, times e to the negative 2x squared, plus the derivative with respect to x, plus the derivative with respect to x of e to the negative 2x squared, of e to the negative 2x squared, times x. So this is just the product rule right over here, derivative of this, of the x, times e to the negative 2x squared, plus the derivative of e to the negative 2x squared, times x right over here. So what is this going to be? Well, all of this stuff in magenta, derivative of x with respect to x, that's just going to be equal to 1. So this first part is going to be equal to e to the negative 2x squared. And now the derivative of e to the negative 2x squared over here, I'll do this in this pink color. So this part right over here that is going to be equal to, or just apply the chain rule. Derivative of e to the negative 2x squared with respect to negative 2x squared, well, that's just going to be e to the negative 2x squared. And we're going to multiply that times the derivative of negative 2x squared with respect to x. And so that's going to be what? Negative 4x. So times negative 4x. And of course we have this x over here. We have that x over there. And let's see, can we simplify it? Can we simplify it at all? Well, obviously both of these terms have an e to the negative 2x squared. I'm going to try to figure out where this is either undefined or where this is equal to 0. So let's think about this a little bit. So let's see, if we factor in e to the negative 2x squared, put that in green, we're going to have, this is equal to e to the negative 2x squared times, we have here 1 minus 4x squared. 1 minus 4x squared. So this is the derivative of f. Now, where would this be undefined or equal to 0? Well, let's see, e to the negative 2x squared, this is going to be defined for any value of x. This part is going to be defined. And this part is also going to be defined for any value of x. So there's no point where this is undefined. Let's think about when this is going to be equal to 0. So you have this product of these two expressions equaling 0. E to the negative 2x squared, that'll never be equal to 0. If you get this exponent to be a really, I guess you could say, very negative number, you will approach 0, but you'll never get it to be 0. So this part here can't be 0. But if the product of two things are 0, at least one of them has to be 0. So the only way that we can get f prime of x to be equal to 0 is when 1 minus 4x squared is equal to 0. So 1 minus 4x squared is equal to 0. Let me rewrite that. 1 minus 4x squared is equal to 0. When does that happen? And this one we can just solve. Add 4x squared to both sides. You get 1 is equal to 4x squared. Divide both sides by 4. You get 1/4 is equal to x squared. And then, what x values is this true at? Well, we just take the plus or minus square root of both sides, and you get x is equal to plus or minus 1/2. Negative 1/2 squared is 1/4. Positive 1/2 squared is 1/4. So if x equals plus or minus 1/2, f prime, or the derivative, is equal to 0. So let me write it this way. F prime of 1/2 is equal to 0, and you can verify that right over here. And f prime of negative 1/2 is equal to 0. So if someone asks what are the critical numbers here? Critical numbers, they are 1/2 and negative 1/2.
You got this. All right. Promise me when you got home, finish watching and learning the following concepts and illustrations on day number 11. It just take you minutes for each, and then you could have a very good understanding of the applications of these critical concepts. All right? So I will see you back here next week, but first of all, allow me to remind you, I need to take attendance, and I showed you your team identity before I let you go. Wacky, are you here? Wacky, not here. Johnson, thank you. Alex, not here. Stella, thank you. Viviana, thank you. Jordan, thank you. Star, thank you. Chaos, thank you. Novia, thank you. Luis, thank you. David, thank you. Sinchun, this is not here today, right? All right, this is not here today. Viola, thank you. Candy, thank you. Mei, thank you. Iris, thank you. Bella, thank you. Cindy, thank you. Vivian, thank you. Patrick, thank you. Jeanette, thank you. Ivy, thank you. Celia, thank you. Michelle, thank you. Lizzie, Thank you. And then, right. Doris, thank you. Kelvin, thank you. Jeremy, not here today. Andy, not here today. Okay. Oh, Andy is here. Thank you. Right. Now, you're supposed to tell me your team identity in week number 6, okay? In week number 6. This is week number 8 already, okay? So in week number 6, when you click on the public online discussion forum here, you see there is something called team pair nominations and confirmations. So far, I just got 4 responses, okay? So you need to tell me your team identity by clicking the reply button on my message and copy and paste this table down there. I will set up the team discussion forum for you so that you can talk with one another to inquire about the homework problem. And the most important thing of this forum is starting next month after the submissions of your work and your midterm, you will do project. Alright? Remember, that's the project time next month. Make sure you send me your team identity right here. Week 6, topic online discussion forum, team pair, nominations and confirmation. No later than tomorrow evening, okay? That's it for today. Thank you very much for coming back. Hope you enjoyed this class. Make sure to review the material day number 11, alright? Next week, we'll go to another part of the applications of derivative called the approximations, alright? See you. Alright, have a good week. Okay, bye-bye.